Right, we're on the air. Okay. Good afternoon, or whatever time it is in your place. My name is Bernardus, and currently I am learning about undefined behavior. As you can see in my GitHub repository in Engineering Roadmap, I created this issue which has the documentation of everything I learned during the week. From day 1, I learned about C. Day 2, I learned about interpreted and just-in-time compiled languages. And on the last day, yesterday, I learned about Rust, how to get C performance with the safety of modern languages. And today, day 4 and conclusion, we'll compile everything into a single documentation, which is this video, or as you can see, a comment I just made 19 minutes ago. Oh my lord. Okay. So without further ado, let's get started. So you might ask, what is undefined behavior? As its name suggests, undefined behavior is when a program doing something undefined in the language specification. So it's the program doing something that should not happen. So when does that happen? It happens when a programmer breaks a set of contracts the compiler sets in place. So what kind of contracts are the compiler enforcing? One thing you need to know before we go further is that the C or C++ compiler in that case deem that the programmer, we, are perfect. So they promise they will give the best performance, but deem us to be perfect as well. So when undefined behavior happen, one of two things will happen. The best case scenario is the operating system stopping you. Why is this the best case? Because in production, it is better to have the program stop rather than it corrupts your memory or database. So the program will crash when accessing memory that's not allowed or interfering with another program. So a program is given a sandbox of memory. As long as you're inside, you're good. But if you step outside, the memory management unit will freak out and send a signal to the operating system to terminate the program immediately before it corrupts another program. So the second case that will happen is a random value. The program will continue to execute. However, the behavior will be unexpected or undefined. For example, it may print 0 instead of the supposed value, or out of index array will print a garbage value that's inside the sandbox of your program's memory, or whatever value that was that was there before your program used it. As long as it doesn't break one of the operating system's rule, this will happen. And the third case is the worst case. It's the compiler optimization. As I've said before, the C or C++ compiler promise to give you the best amount of performance. However, they might skip checking. I'm a bit like, so let me explain it more clearly. So let's say a rule in C that a dereference pointer cannot be null. So if you check if a pointer is null after you use it, the C compiler might skip it altogether. So as you can see here, C or other compiled languages were designed to run as fast as possible, and the compiler demands the program is perfect, as I've said before. Hence, they optimize. The if checking may get removed, and if it does happen, which is if the compiler optimization does happen, it will lead to either operating system stopping you, which is the first case, or continue with a corrupted program. It might reorder function calls or doing something undefined. So from this knowledge, from the first day, we can infer that other interpreted languages have some sort of guardrails. It can be garbage collector, the interpreter itself, or the virtual machine, or whatever, protecting the memory from being corrupted, which makes sure no undefined behavior can happen. So let me clarify a bit. Undefined behavior can happen. It can happen in like interpreted languages. But for example, when in a Python you call a C function, it can trigger undefined behavior, but it's not the Python itself, it's on C. Same case anyway. So in C programming, always validate your data before you use it, as I've said before. So you need to validate before you use it. So before you dereference a pointer, you check where it's null, not after you assign it to a variable. Undefined behavior is random. It's hard to make it feasible, and it may result in one of the three endings we discussed before. It's not kind of random, it's undefined. It's the same thing, but yeah, that's pretty good. So moving to day 2, after we learned about C, we learned about interpreted and just-in-time compiled languages. Something like Python, Java, JavaScript. So there are like 4 types of languages as I know. The first one is purely interpreted languages. This type of languages. Before we go further, let me show you a bit something. Yes, this is a This is a flowchart I make about how languages take your source code and. So the first one is compiled languages, C or C++. In start, the program. This is the start of the flowchart. The compiler takes your source code and compile it into machine code. And after it is compiled, you get an executable you can execute in your machine. As you can see here, there is no checking, there's no memory checking, there's no source of like making sure that your variable lifetimes and everything is safe in your code. You need to do it manually in your source code. Right? So if undefined behavior happens, yes, one of the three things will happen. But the second one is purely interpreted. It takes your source code and interprets it line by line. So where does the interpreter? So the one managing your variable lifetimes and safety is your interpreter itself. It can call malloc, it can call free, it can do anything it needs to do. Not every time, not every line, but whenever it is necessary. In purely interpreted languages, the entity managing your variable's memory lifetime and sets of contract are handled by the interpreter. The interpreter, often written in C, calls functions like malloc and free to manage memory and check your code safety line by line or instruction by instruction, may I correct, enforcing the sets of contracts. So the next kind of languages we'll learn is interpreted but with bytecode and virtual machine. A bit of fun fact, languages like Python, which people think is a purely interpreted languages, is actually an interpreted with bytecode and virtual machine. So the main example we'll use in number 2 is Python. So actually, something you'll call an interpreter in the internet is actually a language implementation. Is a full language implementation. It consists of 2 parts, a compiler and a virtual machine. Yes, an interpreted languages have a compiler. Inside the virtual machine, it consists of an interpreter of bytecode, garbage collector, and etc. that you need. This type of language takes your source code and then compile it first into bytecode. Something that will then be passed into the virtual machine. The virtual machine will then pass the compiled bytecode into the interpreter. It will interpret the bytecode line by line, while other programs inside the virtual machine like the garbage collector will manage the memory and make sure there are no dangling pointers, etc. etc. So when the program finishes executing, the used memory is gradually released. So when a program is finished executing, the memory is gradually released, leaving a blank spot for other programs to live in later. So, as I've said, the undefined behavior prevention is in the virtual machine, managing your variables memory, lifetime, and sets of contracts in the virtual machine. So the third kind of languages is just-in-time compile, something like Java does. So it's pretty much the same as virtual machine and bytecode interpreted. The only difference lies in here. So as the name suggests, just-in-time compiled. So it is compiled in time. At first it runs slowly like interpreted languages, but over time it can get faster. How? This part. In this if is a part executed frequently. So it checks if a part of code called hotspot is executed frequently, it will get compiled into machine code. And if in runtime it turns out it isn't safe or unsafe, it'll get the optimized back into interpreter mode. So the only difference between just-in-time compiled or JIT and VM bytecode interpreted is this part. JIT is more efficient. So now we go back to C and C++. The reason I started this journey. For compiled languages, they take all your source code and translate it into machine code into an executable your machine can run. So how do they do? How do they prevent undefined behavior? Not at all. It is your job as a programmer to take care of the memory and prevent undefined behavior yourself. So they don't have an undefined behavior prevention. The compilers read the code and deem you the programmer as perfect. In return, they will perform as fast as possible. They optimize aggressively, sometimes even reorder functions and remove if statements in the name of performance. Not as always, but when you break a set of contracts, as we said, undefined behavior. Rust is a unique case, which we'll talk about later. So, the conclusion, how does operating system stop programs from going rogue? In the case of interpreted or just-in-time compiled languages, every program is contained within their sandbox, as I've said. Every program has a sandbox. As long as you don't step out of it, the OS won't stop you. But for unsafe compiled languages that have direct access to the memory of C or C++ in instance, the OS stops them using the memory management unit. This is what I talk about. I use the word I talk about it so much. Okay, whenever a program steps outside of its boundaries, the MMU or memory management unit, a part of the CPU, detects this at the hardware level and then sends a signal to the operating system to immediately stop or kill the program before everything else is corrupted. So that's pretty much the second day, the documentation of the second day. Now we'll move to the elephant in the room. Yes, Rust stations. So a bit of pre-word before I enter Rust. I don't really deep dive into Rust that much. I only learned how does Rust prevent undefined behavior, not deep dive into how the compiler does things like LLVM, abstract tree syntax. No, not at all. I just explain how Rust prevent undefined behavior. So Rust is a unique case in my opinion. In the beginning, it takes your source code .rs files. Then the parser, type checker, and borrow checker takes your code. Is it safe or no? If the memory if it is not proven that it is, how do you say? If it is proven that it's not a memory safe program, it will be a compile error and immediately stops compiling. But if it is proven that it is memory safe, it'll do one more check. Does your program depends on runtime values? It checks to prevent something like out of array bounds or overflow, buffer overflow, something like that. If yes, in your binary it will add a guard which will trigger Rust panic runtime later. This runtime, we'll talk about it later. In the end, it'll compile into machine code. You'll get an executable at end. Now, this is Rust runtime. I specifically made this for Rust. As is a greedy man. Okay, in the beginning, you run your executable, and in the runtime, you'll check does the guard exist and is the condition violated. If no, the code is executed successfully. The program runs happily ever after. The developer will try. If no, it will trigger a runtime error called Rust panic. And so how does Rust get the C performance with modern languages safety? So the first one is obviously Rust is compiled, so no overhead of an interpreter. Yes, I said that the compiled languages like C or C++ doesn't have undefined behavior guard, but Rust is a unique case. It is compiled into binary and native code which the CPU can directly understand. There is no overhead, as I said, of an interpreter like interpreted or JTL languages. This is the secret to speed. Yes, Flash. Next, Rust manages memory differently. If in C or C++, you as a programmer need to manage the memory manually, in Rust and in the interpreted languages or just-in-time compiled, they have something like garbage collector to manage your memory for you. In Rust, the case is different. Now, for safety, Rust moves checking variables memory and lifetime during compile time, so before it hits production or runtime, resulting in a very long compile time, which people complain about, but checking that your code is safe, no undefined behavior, no REST condition, etc. A bit of a side note: Rust can have undefined behavior, but inside an unsafe scope. So if it is normal Rust, no undefined behavior, no REST condition. But if it is unsafe Rust, who knows? The compiler can So if your code is already proven safe, the compiler can optimize aggressively, resulting in a very fast performance. So another quirk about Rust is the variables immutability. Variables in Rust are immutable by default, resulting in the compiler being allowed to optimize aggressively via now having to put the variable this is typo, not having to put the variable in RAM since the value is down at compile time, either baked into the executable itself or put in the CPU register, which is faster than putting it inside RAM. Now we got into the bread and butter of Rust, ownership and borrowing. Instead of a raw pointer in C, Rust takes a different approach, ownership and borrowing. Yes. Instead of poking memory address manually, Rust gives something called reference. You can reference a variable in Rust and dereference it to either change or read only. Once you let another variable or owner borrow a value, the first owner cannot be used as the value is being borrowed by the borrower. So you cannot use, so the first owner it's not voluntarily, we make him give up his value to the borrower. So we cannot use the owner. This is a snippet I made. This is function main. Now this is a mutable variable, x equals 32, and y is a mutable reference to the x. So when y changes 32, the x will change again to 32. Oh my god, why did I do it? So as I've said, the first owner cannot be used. Like this example, print line the value of x is x. Cannot do because the value is borrowed by y. Yes. Because the value is borrowed, hence x is kind of useless. Not useless, but it is being borrowed. So this is allowed. This will print the user-friendly value. The compiler, since y is an address to x, and since this is pretty print, the result will be to follow the y address and print whatever inside of it, which is the value of x. So next, This is directly printing the memory since we put inside the bracket colon P. And the next one, this is the reference, as I've said, read only. Now, this is a unique part in Rust case. No can do, only one mutable borrowing is allowed in one scope. It is to prevent data race. So, multiple mutable references are not allowed. It's not allowed to prevent that race. So this is another case. If it is a immutable borrowing, you can borrow as much as possible since it won't be a data race since it's mutable. You can change anything. They point to the same address, they point to the same value. Now borrow checker. This is a part in which the Rust compiler checks is your code safe or not. The borrow checker's job is to ensure the sets of constructs are fulfilled by the program has finished building during compile time. For example, the rules I've said before, only one mutable borrowing at one time or scope, and this ensures maximum optimization for the final executable. However, Rust compiler and Rust panic. When the borrow checker can guarantee something safe, like accessing an array index or integer overflow, the compiler inserts a tiny guard into your binary, and in runtime, if anything crosses this guard, it will throw an unrecoverable runtime error, also known as Rust panic. So as I've said before, if it is dependent on user or runtime values, it will add a guard. Let's take a look at this example. This is standard input output. This is the maximum value of U32 data type, and this is the maximum value of integer 64. If we add 1, this will result in a runtime error or Rust panic. Also, or it might wrap to 0 in release mode because Rust optimize might, so if it is overflow, it wraps back to 0. So this last one is also Rust panic. We only have 0, 1, 2, and 3. The length is 4 and the maximum index is 3. So if I input anything over 3, it will throw a Rust error or Rust panic. This is the maximum length I will go for undefined behavior in Rust. I will dive deeper in the future, but for now, as I'm focused in learning C and becoming a better programmer, this is enough and sufficient. So now I know how does modern languages prevent undefined behavior. So that's pretty much for this week's documentation of my learning. Thank you very much for watching and see you next week. Next week we'll talk about pointers usage. Yes, the bread and butter of C now. So see you next week. I'm Bernardus, signing out.